on the weekend? Have those companies coming on set?
And this must have been only one day instead of two.
Yeah, exactly. How does that make sense? What happens? Doesn't even really
So guys, today we'll have a small class. I think students, some, I get 2 or 3 emails, so the rest of the class email will not come. So I think maybe one's coming. I think there's job fair today, and the other stuff is out of state. So today we will finish chapter 24, and we will finish it today. You can start working on the practice questions. We'll make them available by the end of today. Chapter 24, you can start with this if you want to start preparing for the exam. The second exam will be, for now it's supposed to be week 8. And it's possible to move it to week 9 as well for the exam. But let's see first if we can complete everything on time. So for capacitors, quickly I'll remind you with what we did yesterday. If we have 2 plates parallel to each other, this is the capacitor. It has a capacitance C, which is epsilon 0 area over D. This number, after you do the calculations, even if there is no voltage, this capacitance is a unit called farad. And this is coulomb per volt. So let's say if it is 1 microfarad, for example, that means it is 1 microcoulomb per volt. If I apply 1 volt, it will be 1 microcoulomb. 2 volts, 2 microcoulombs. And if you, of course, now this is empty, there is no charge, but still see this is the number. Now if you connect this to a voltage V, then we'll have charge on each plate, and this charge equals the capacitance times the voltage you apply. Also, we have electric field, which is voltage over distance. The distance is the between the 2 plates, and this is also sigma over epsilon 0. You can use either way. Now to change C, we talked about this yesterday, we spent most of the time. You can change C under 2 conditions: battery connected, in this case, if we change C by changing D or A or epsilon, then the voltage stays the same because the battery will keep the voltage. We did the example when we reduced the distance, and C increases, and then Q going to increase as well. If you decrease this, you go to decrease. Because when the battery connected, B stays the same, and whatever you do with C, that's going to do that same thing happening to Q. The other case, if we disconnect the battery, and then change C. So if you remove this, and you double the distance, reduce the distance, then if C increases, V is going to change because this stays the same. But now this is going to go down. If this is down, it's going to go up. So we did these 2 cases, and we did the example last time. Actually, there's many applications on this. And the idea, one thing I can just things that come to my mind. You know the keyboard for the key for the keyboard, this is actually a capacitor like this. Same idea as this. So the keyboard, we have under this, we have a plate. This is the fixed plate. Another plate, a distance between them, and this plate is attached to the key. That's what you see. You click on this. So when you click on this, because this is a capacitor, there's a material between these two blades. And by clicking on the key, that is reducing the distance between the two blades, keeping the voltage constant. The voltage between these two blades stays constant. So that's the same case like this. So keeping V constant. When you click on this, you reduce the distance. Increasing C, that will increase the charge. So there's more charge on this coming from the voltage, and this is attached to create a signal, charge signal, and this signal can go to another circuit to analyze this, and that will be consistent with the key you have. Each key has different distance between the two plates, different D, and different D makes a different C, and that C is especially for each key. For each key we have different C and that different signal. So this is one application for capacitors. For this case, when we have the Q constant, they do microphones for this. Microphone, you know, the sound wave, when you speak, air molecules, they will be compressed, and then they will be far away from each other, and again compressed. So when you speak in the front of a membrane, this is going to vibrate or to move. So this membrane has a charge. So they place charge on this membrane, and this is isolated. So this doesn't, so the charge is constant. And then they place this in the front of another sheet or another plate, and this is connected to a circuit of voltage. So this is a capacitor. Now when you speak in the front of this microphone, this is going to move closer. And that's changing capacitance because D changes. And that's changing the capacitance, keeping the Q constant. This is isolated. It's not touching anything. Then that's going to change the voltage between these 2 points. And the same frequency you speak with, that will be the same frequency as the voltage changes. And that can be transferred to a signal and that transferred again to a voice. So that's also another application. Actually, many applications. The touch screen thing it is a capacitor. When you touch the screen of your phone, there's many layers, and there's a capacitor. You change the capacitance, and that will transfer the signal from one to other. Even the way how that's in medical field also. The way how if you do a stimulation in your nerve, the way how it goes from one point to another point, it is the same idea as this. If you have, let's say, a membrane of a cell, a cell is inside of the cell, is the outside of the cell. This membrane, it is like a capacitor. So inside we have negative charge, outside we have positive charge. This is due to the ions for our body. And now, if you take this as a capacitor, and the material between these two plates, which is the material of the membrane, when you do any stimulation, let's say you did kind of a needle, touch this, that's going to change the voltage at this point. It's called the membrane potential, because you're giving a charge. And this changing the voltage, so Q equals CV. Now you change voltage, but C is constant. Now this is like a third case where we keep the C constant, because this distance stays the same and the material the same. And because you increase the voltage, that's going to increase the charge. So we need more charge to be here. From where we get this charge? We get this from the other parts of the around this point. So when this charge moves here, what happens? Now the charge decreases in this region, still stays the same, C. But that is going to change the voltage here. So basically you create a change in voltage here, and that's now here. And this more charge will go to this point and transfer here. So the voltage is going to transfer from one point to another point just because the charge keeps moving, because you do change in one point only. That's the way how the signal, or if you have a nerve, if you do any stimulation, that's how it travels from one point to another point in the inside. So this is like, beside the applications I mentioned the first time when we talked about this, mainly for pulsing, because the capacitors, you can charge it. We'll talk about charging, discharging mixed charger. But if you charge this, take time to charge, then you discharge it in a shorter time. That will increase the amount of power you can get, because you discharge it in a shorter time. Last time, also at the end of the lecture, in the last 5 minutes, we talked about changing this. by adding an insulator between the two plates, different than air. And we kind of talked about how having this dielectric, we call it dielectric material or insulator, how this changes the capacitance or electric field. So let me remind you of this. So this is under dielectrics. So we have the plate, or the two plates. Now we have C0, and here I'm going to use 0 or C0 to indicate that we have air between the two plates. And this is epsilon 0, area over D. And now if you connect this to a voltage, I'm going to call it V0 because we have air. This is going to create Q0 on each plate. And the electric field between these two plates, it is V0 over D. That's electric. Also, that's an air capacitor. So everything is the same. I just add 0 to indicate that we have air between the two plates. Now, if we insert a dielectric material, like an insulator between the two plates, let's think of having a block of wood between these two plates. Then the material, or the atoms of the material of the insulator, is going to polarize. Positive, so the atoms will be something like this. Negative charge goes toward the positive plate, positive goes toward the negative. So we have all of these atoms, because we have many of them. Now these charges will become neutral, because they will be overlapping. Same thing here, same thing here. At the end, we end up with only charges on the surface of the dielectric. The surface close to the positive plate will be negative. The surface close to the negative plate will be positive. And that will create another electric field in the opposite direction of this electric field. So now if you measure the electric field between these 2 points, it will decrease. And the new electric field, so I call it E nu, it is E0 minus E. Because E0 is the electric field without dielectric. E nu is the electric field with dielectric. And as you see, with dielectric, it's smaller than without by this amount, which I don't care about this amount for now. We can write this as E0 over K, where K now called the dielectric constant. And this K is always larger than or equal to. It is 1 for air, and for any other insulator is going to be more than 1. So the electric field is going to decrease. When you insert dielectric, electric field will decrease. What about the voltage? Of course, if the voltage between the two plates stays, or the battery connected, it stays the same. But what if I disconnect the battery? What is the new voltage now? After I disconnect the battery. Now, the new voltage, it is the electric field times D, the new electric field. And the new electric field, it is E0 over K times D. But this, E0 times D, it is just V0. So the new voltage will be V0 over K. So the new voltage also is going to drop. So initially I have V0, after I put the dielectric, if the battery is not there, then the voltage will drop to V0 over K. So E decreases, V decreases. Now what about C, the capacitance? Now remember the capacitance C, it is Q over V. So the new C, the new Q over V. But because the battery is not connected, this Q stays the same. Remember we said that the battery is disconnected, the Q stays the same. So this Q nu is same as Q0. And V nu is V0 over K. So the C nu, the new value of the capacitance, it is K. Q0 over V0 is just this C0. So that means the new capacitance, it is the capacitance without dielectric times the constant K, which means now C is going to increase because remember K is larger than 1. So when you have a dielectric between the two plates, that's going to increase their capacity. We can go to the capacity. So that's why to have or to increase the capacitance, one way to add a different material than air between the two plates. So the air capacitor is the smallest C. I don't know if you know this, but for the batteries of your cell phone, you have liquid inside. These are like, if you look at the battery, it's like just a black plastic bag. You cannot open, I mean, if you open it, it has solution, will leak. And it's many layers, which is like capacitors. And then in between, there is a liquid solution to increase K. By the way, water, for example, K for water is about 80. So if you add water between these two plates, the capacitance will increase 80 times. So that means you can hold more charge. And in the batteries of the cell phones, they add the solution to increase the capacitance, so we can put more charge on the plates. And the thing is with these capacitors, why it's dangerous to play around with them, because especially if they have charge, and the plates are very close to each other. So this is like the whole thickness of the battery, maybe 5-6 millimeters, and it has maybe 4 or 5 sheets. So the distance between the sheets are very, very close. So if you, they touch each other, that's going to make a discharge, and that will make it very hot, and that can burn. Because that's the way how they can get in fire, because the charge or the two plates kind of touching each other, and that will make a discharge, and that will make a spark, and then that will be a problem. So the dielectric material, they increase the capacitance using this. I'm going now to do one example. So basically the new capacitance, I can have this also as K epsilon 0 area over D. Right, so that is, of course, if we have K, if it's air, as we used to do before, so this is going to be just 1. If we have another material, we multiply by this constant K. So in the example I'm going to do now, I will use the same numbers we used yesterday. So the first part I'm going to remind you with the same example, so you don't have even to have the numbers, because we already did this yesterday in the example. But I'm going to add to it part 2 when we have a dielectric and see how this is going to change. So in the example we did yesterday, there are 2 plates. This 20 centimeter, same numbers we used in the previous class, and this D is 1 millimeter. So I want to remind you of the numbers we did. We already did the calculations yesterday. First thing we asked about C, and we'll go now C0, because we have air between the two plates. And this is epsilon 0 area over D. Area is 0.2 times 0.1, epsilon 0, 8.85, 10 to minus 12, and this 1, 10 to minus 3, and we got 1.77 times 10 to negative 10. Okay, you can look at the example we did yesterday, or you can do the numbers and get this answer. The second question, if we connect this to 100 volt, what is the charge on the plates? So this is Q0. And we found this C0 times V0, and we have this 1.77 times 10 to the minus 8 coulomb. We did this also. Then what is the electric field? is 0 between these two plates. And this is V0 over D. And this is 100 over 0.001 meter, which is 1 times 10 to 5 volt per meter. And then finally we ask about the energy, U0, which is half CV squared. And if you do the numbers, C0 is this and V is this, we got the 8.87 times 10 to negative 7 joules. You can look at the numbers from yesterday's exam. So that's what we did. Then yesterday what we did, we assumed, if the battery connected and reduce the distance, find 4 values again, and then disconnect the battery, reduce the distance, find the values again. That's the example. Today I'm going to include dielectrics between the two things. So the first thing we are going to do for this system, if the battery is connected, dielectric material where K equals 2, so we have it's like a wood, inserted between the two plates. So imagine we have this dielectric material, K equals 2, and we keep the battery connected, and we slide this between the two plates. Completely filling the space between the two plates. Now we have a new system with dielectric inside. What is the C0 or C nu now? What is the C of this after we put the dielectric inside? What is the Q0, Q nu, V nu, E nu, and U nu? So we need to find these values after we put the dielectric between the two plates. So what happens to the C? With dielectric is going to increase and going to be now K times C0. And K is 2, 1.7710 to minus 10, and that is 3.54 times 10 to negative 10 farad. Okay, so the capacitance will increase because of the dielectric. The new, now which value will stay the same? Q or V based on this, battery is connected. Which one? The voltage, right? And the voltage will be as V0, which is 100 volt. And now the Q, it's C nu, V nu. C nu is 3.54 times 10 to negative 10. And the new voltage still is 100, and that's 3.54 10 to negative 8 volt. Right? So this will be the new charge. And as you see, we have the charge is going up compared to this. And this charge is coming from the battery, because the battery is connected. What is the new electric field? We can use V nu over D, because V is 100, D is 0.001, that is 1 times 10 to 5 volt per meter. So this is the same as the voltage we have here. It didn't change. Common mistake, can we use this? E as sigma over epsilon 0? Can we use this equation for this case? No, why? Because the epsilon 0 is not the same now. This is for air, but now we don't have air. We have the dielectric material. So if you want to do this, you have to multiply this by K. You can multiply this by K, then that's fine. I see this all the time in the second exams when I ask for electric field. Many use the sigma or epsilon zero, but this is not true for the case when we have dielectric material. And for the energy, it is half C nu V nu squared. Half C is 3.54 times 10 to the negative 10, and V is 100 squared. That will be 1.77 times 10 to the negative 6. So now the energy increases from this number to this number. We mentioned this yesterday. This increase in the energy is due to the work you need to do to insert the dielectric material. So basically, you need to force it. Because the system, when you put this inside, energy increases, and the system will not like it. So you have to kind of force it to go inside. And if I ask you how much work you need to do to insert this inside, this work will be negative delta U between these two energies. Now the second case, if we disconnect the battery, so now the battery is disconnected, then the dielectric material inserted between the two plates. So for this part now, we first disconnect the battery, and then we slide this into the two plates. And we need to find, same thing, the values of the C nu, Q nu, V nu, E nu, and U nu. So now for the C, it's going to be same as this. Has nothing to do with battery connected, disconnected. So this is going to be also 3.54 10 to negative 10 farad. Now because we disconnect the battery, then the charge will be constant, the same as this, which is 1.77 10 to negative 8. Cool. And based on this, we can find V, which is Q nu over C nu. That is 1.7 times 10 to negative 8, and C is 3.54 10 to negative 10, and that will be 50. So it's going to be 50 volts. And for the electric field, it is the new voltage over the distance, which is 50. Distance is 0.01, and that is 5 times 10 to 4 volt per meter. So the electric field decreases. And for the energy, it is half C nu V nu squared. That is half 3.54 times 10 to negative 10, and now the volt is only 50. This is going to be half of this. So it's 4.4 10 to minus 7. So actually, as you see, the energy is going to decrease. So what do you think is going to happen now? We said for this case, because the energy increases, you have to force this to go inside, because that's against what the system likes. The system stays at lower energy, so energy increases. The system tries to resist that, so you have to by force to do it. For this case now, this is less. So do you have to force this to go inside? What happens? Actually, it's going to kind of a magnet attract this. So when you went this way, it's going to kind of suck this and go inside. Because that is to the system, it is something the system likes to go in the lower energy. So this basically it will take this. Actually, you need maybe to hold it from this instead of just going inside. So for the dielectrics, And we always use them to increase the capacitance. And this example, you will see at least one example on diagram similar to this one with the practice questions, for example. Any questions before we move to the next topic? We have one more topic from chapter 24. We will do it about 20 minutes. We'll do this, which is basically the way how we combine capacitors. We have two ways of combining capacitors. One, we have series and parallel combination. So let's talk about these two ways of combining capacitors, and then we'll do one example. So we have two ways to combine capacitors. The first one, I will talk about capacitors in parallel combination. Now in circuits, for the diagram, if you see two lines with the same length, this represents a capacitor. Each plane goes the same area. And when you see one long line and one short line, this is the battery. The long one is the positive, the short one is the negative. And when you see lines like this to connect the circuit, these lines in the actual circuit, these are wires. You connect for the single circuit, like a wire from negative side of the battery to this plate, positive to this two wires. If you have another capacitor, like this, C1 and C2. Now, if you have any point, and you know the voltage at a specific point, let's say this point. Let's say the voltage here is A, 5 volt, 10 volt, whatever. And if you go through the wire, at any point, it's the same voltage. So this voltage is let's say A, this voltage is A, this voltage is A. As long as you are not passing through or crossing through any element, voltage will not change. By element, I mean, imagine you have another capacitor here. So if this is A, you keep going, this is A. But now if you go to this point, your voltage is going to change because you're passing through the capacitor. The capacitor will either increase your voltage or decrease your voltage. So there's going to be a different voltage, B. But if you don't go through any element, and by element I mean either capacitor, resistance, battery, inductor, later we'll talk about all these things. So this is not going to change. So this is A, this is A, this is A. Same voltage. And now you go to this one, this has a different voltage, B, this is B, and this is B. So as you see, the voltage between these two plates is AB, AB, AB. So these two capacitors, they have the same voltage, and which is the same as the voltage of the battery. So that means V equals V1 equals V2. So when they are in parallel combination, the two capacitors have the same voltage. For the charge coming from the battery. So that's the source of the charge. So this charge is Q coming from the battery. And as you see, this plate and this plate both are connected to the same battery. So this charge is going to divide between these two plates. So whatever this battery provided, they will be divided between these two plates. So Q is Q1 plus Q2. So in parallel combination, the voltage of the two capacitors will be the same, but the charge is going to divide between the two capacitors. Now, if we need to replace these two capacitors by one that will do the same job as both of them, we call this capacitor equivalent of both. So if I want to do a circuit with only one capacitor, and this circuit is equivalent to this, which means these two capacitors, they take a certain charge and certain voltage from the battery. This one will do the same thing. C equivalent will take the same charge and the same voltage from the battery. So it will do the same job. This equivalent, and if you look at this, QVC, C equivalent, it is Q over V, which is the Q of the battery over the voltage of the battery. And since the Q is the Q1 plus the Q2, Q, it is C equivalent times the voltage from this. So Q equals Q1 plus Q2, but the Q is C equivalent times voltage. Q1, if the voltage here is V, which is the same, or V1, and the Q1, that is V1 C1. And this one is V2 C2. But V equals V1 equals V2. So that means C equivalent, it is C1 plus C2. So if you want to find the equivalent of these two, you just add C1 plus C2. So this is 1 microfarad, 2 microfarad. I can take these two and replace them by 1 equals 3 microfarad, and this will do the same job as both of them. So this is called the equivalent of the two capacitors in a variable combination. The second way of combining the capacitors, I will talk about the second way, then we'll do one example. If they are in series. For this combination, we have the two capacitors are connected with one wire, like this. So they are connected with one wire without a junction. So that's the way how we determine if these are in series or not. So if these two plates are connected with one wire and there's no junction, then they are in series. Like if there's a wire like this, there's a junction. These are not in series anymore. So it has to be just one wire without any junction, then they will be in series. For the voltage, if this voltage is A, this is A, then it's going to be B, then this is B, then this is C, and this is C. AB, BC, AC, different voltages. So the voltage here is not the same, but the voltage will be divided, which means whatever voltage given from the battery, it will be divided between both. Like for example, this is 10, 2, 8, 10, 3, 7, 10, 4, 6. So it has to be divided. So now V, it is V1 plus V2. So now the voltage is divided. There's the charge divided. For the charge, now as you see this capacitor, C1, the only plate that's connected to the battery is just one plate. So this charge, Q, from the battery will be Q here. So the charge on this capacitor will equal the charge of the battery, because that's the only plate that's connected to the battery. Now, how do we charge the second capacitor? Now remember, this plate is a conductor. This is also another conductor, and this wire is a conductor. And what do you have in between here and here? Insulator, right? So these two, or this system of the two plates and the wire, these are kind of separated. And they have free charge because they're conductors. So we have negatives and positives everywhere. Now, when this charge becomes positive, is that going to affect this? Yes, because they're free charge. So this positive is going to attract the negatives and repel the positives. So the negatives, if this is 1 microcoulomb, for example, it's going to attract 1 microcoulomb negative, it will repel 1 microcoulomb positive. So what's the charge of this? Same as the charge of this. Same as the charge of the battery. So the two capacitors in series, they have the same charge, which means Q equals Q1 equals Q2. So now they have the same charge, V divided. In series, in parallel combination, they have the same V, but Q will be divided. To find the equivalent, if you want to replace these two by 1, C equivalent, for the series combination we use 1 over C equivalent, it is 1 over C1 plus 1 over C2. Okay, so that is the way how we find the equivalent. We take 1 over C. So for series combination, we need to know that they have the same Q, but they will be divided, and this is the way we find the equivalent. For the parallel combination, they have the same V, but it will be divided, and we just add the two capacitors to find the equivalent. So now I'm going to do one example on the combination. I will do the two combination in one example. So in this example, we have 3 capacitors. Let's take this C1, 1 microfarad, C2, 2 microfarad, and C3, take this as 6 microfarad. And this voltage, let's take this as 10 volts. Okay, now we need to find the equivalent of these 3 capacitors. As you see, this and this, they are in parallel combination, so we combine them first. C1 parallel to C2, then C1, 2 is C1 plus C2. So this is the combination of C1 and 2, and that would be 1 plus 2, 3 microfarad. So I can replace these two by one capacitor which has 3 microfarad capacitance. Now the new circuit is this. So this is C12, which is 3 microfarad, that's the new one. C3, it is 6 microfarad, and this is B, which is 10 volts. So now the circuit from 3 capacitors to 2. Now this and this, they are in series. So now we have C12 and C3, they are in series. And to find the equivalent, we use 1 over C equivalent, 1 over C1, 2, plus 1 over C3. So that is 1 over 3 plus 1 over 6. Because this is 2 over 6 plus 1 over 6, that's 3 over 6. And then C equivalent would be 6 over 3, which is 2 microfarad. So the equivalent now is just 2 microfarad. So I can replace these two, or the 3 by C equivalent 2 microfarad, and this voltage is 10 volt. So the answer is 2 microfarad. That's the equivalent of the two capacitors. Now the other question, if we need to analyze the circuit, we know this is 10 volt. But what about the voltage between these 2 points, or these 2 points? What's the voltage here? What's the voltage here? What's the charge on each capacitor? So we need to find V1, V2, V3, Q1, Q2, Q3. So we need to analyze the circuit by finding the voltage and the charges on each capacitor. To do this, you need to simplify the circuit from 3 to 2 to 1, and you start from here, because this is the simple circuit. And we know C or Q equals C times V for any capacitor. So if you know 2 numbers, you can find the third. Looking at this simple circuit, we know the voltage between these 2 plates is 10, and we know the C is 2. I can find the charge. So Q is C equivalent times voltage. That is 2 times 10, which is a 20 microcoulomb. So I know this capacitor has 20 microcoulomb. I know the voltage is 10, I know the C is 2. So I have everything for the circuit. But my question is, to find these numbers not here, I have to go back to the first one. So now I will go backwards. I will go from this one to this circuit. And I know this capacitor is an equivalent of 2 capacitors that are initially, they were in series. So if they are in series, do they have the same Q or same V with respect to the equivalent? Same Q, which means Q12 is 20 microcoulomb and Q3 is 20 microcoulomb. And now since I know C and Q, I can find voltage. So now from this I can find V3, which is Q3 over C3. That will be 20 over 6, plus micro with micro cancels, 20 over 6 volt, which is about 3.6 volt, or 3.3 volts. And V12, it is 20 over 3 volt, which is about 6.7 volts. So we have now everything we know about this. QCV, QCV. But again, my goal is to find them here. So now, this one is an original one. So the same numbers we have. So V3, it's 20 over 6. Q3 is 20 microcoulomb. And C3 is 6 microfarad. So we have everything here. See. But now, this one is not the original capacitor. This is an equivalent of 2 capacitors that are initially in parallel combination. And parallel means they have the same voltage as the equivalent. So if this voltage is 20 over 3, V1 20 over 3 volt, and V2 20 over 3 volt. And now, since I know C and V, I can find the Q. So now Q1, it is C1 V1. This times this is going to be 20 over 3 microcoulomb. And Q2, 20, which is going to be 40 over 3 microcoulomb. So now I have the 3 values for each capacitor. So for this type of circuits, you have to simplify it until you get to the first or the simple one. Then you go backwards. When they are in series, they have the same Q. When they are in parallel combination, they have the same voltage. And then you have 2 of them with these values, then you can find the third one using this equation. so with this, I'm going to stop here for today. We are done with this chapter, but I will talk about one thing. I will talk about this in the lab tomorrow. When we have dielectrics, how can we add them in series and parallel combination? And that's part of our lab tomorrow. So we'll send in this in the lab. So I'll see you tomorrow.